So yeah, I just had it dropped me from 97 to 85, which is ridiculous. Yeah. And I was salty about it for like the longest time, but then I looked at the great distribution and I was so
the grade below it's like the average for the finals is like, we get 25% pass, but then you get down to 10% or less than that. You had I think 4 big action passes. It's like a ridiculous amount. They were already programmed.
Well, that's the thing. I've been programming since I was literally a child.
Yeah,
so
that makes total sense. Yeah, yeah. I feel like that.
Yeah.
Okay, let's start. Let me explain the schedule. So today we will talk about power and performance and the power. On the coming Wednesday, we will do a review. I will present 10 questions, problems, most of which you should know them in the homework. And then in the next week, we will, for the Monday, next week Monday, we will have some questions. If you have a question, you can come to this classroom and we can talk about those questions. And then we will have our midterm. So most 90% of questions in our midterm are from that review. I cannot guarantee you will have exactly the same question, but I will just change some number. Any question on that?
And we'll be doing the review in the next class.
Yes, and then next Monday is the Q&A. If you have any question on that review, I give you some time to review those reviews. If you have any question on that, we can talk about those questions in next Monday. And then we will have the midterm. The midterm, 90% of the questions in the midterm are from that review. But they are not exactly the same. I will just change some numbers. Okay, let's start. Because we have some basic concept on the numbers, floating point, integer, transistors, and we also learned something about the assembly language. Now we will study some metrics to evaluate a hardware platform or a combination of a hardware and a software. A system, let's say, we will study some metrics to evaluate a system in terms of performance and power, of course. So the first law we have here is so-called Amdahl's law. So this law is to help you to decide whether you need to upgrade your hardware, some components of your hardware. For example, if you want to buy a CPU or if you want to buy a larger capacity of DRAM, do you want to do that? So this equation can help you to decide. So the speed up is defined as the execution time, the latency, with no enhancement, divided by the latency with those new hardware components. So generally speaking, if you have some new hardware, your system should run faster, which means that you will have a smaller value for this part. Then the speed up should be larger than 1, because the time with the enhancement should be smaller. And enhancement speeds up fraction f of a task by a factor s. So the new time, or the time with enhancement, should be calculated as this. So 1 minus f indicates the fraction cannot be speed up by the new component. F divided by f is the new the fraction if you have those new components. What's the fraction if you have those new components? You use the f divided by f because the f should be smaller, because you actually improve the performance of that component, of that fraction, those fractions, and then you sum them together. So if you have f here, instead of f divided by f, f divided by f, if you have f here, the sum of these parts should be exactly 1, which is the whole task. But since you have this f divided by s, then the sum should be smaller than 1. So if the time original multiplied is a number smaller than 1, then the time new should be smaller than the time origin. And then you can compute the speed up by this equation. I will use a picture to explain this. So this is the original time, which is a 1. Assume that you have $1,000, $1K. Whether you need to upgrade your CPU or GPU, this is a question. Assume this is a game. So after set, time is actually consumed. After percent of the game is executed by the GPU. This is the GPU part, and this part is the CPU. So if you have a new GPU, a faster GPU, then this is the latency. Because you didn't change your CPU yet, so this part is the same, keeps the same, unchanged. This is your new latency. So apparently the game of the latency of the whole game reduced. Then in this way, you need to buy a new GPU. Why? Because if you buy a new CPU, even your CPU can reduce the latency of this fraction to here. Then the total game latency is also super long, because you didn't reduce the latency of this fraction, and the fraction f is actually dominant the whole game. Any question on this? However, if you do not like the game, if you how to say, if you compute some floating point operation application a lot, so this is your CPU. The application has this portion, this fraction on the CPU. Only use the GPU this much. If you have a new GPU, then this is the improvement. So for this type of application, you shouldn't buy a new GPU. A new CPU is a better option for you. So the principle of this law is very simple. You just always accelerate the bottleneck. Identify the kernel, identify the bottleneck, and accelerate only the bottleneck. If you accelerate some non-kernel or non-bottleneck part, then it doesn't help the entire application. So this law can help you to calculate the performance of a CPU. So this part indicates the average execution time of each application, of each program. So this is the average instruction number per application. And then this is the cycle per instruction. This is the absolute latency of each cycle, absolute time of each cycle. So this part is actually your CPU frequency. And this part is cycle per instruction. And this part is total work in the program. I believe some of you may take the algorithm class or the compiler class. So those classes can help you to reduce the overall workloads in each program. Why? Because you reduce the time complexity of each program. You improve your compiler, use the advanced compiler to reduce the code size, the total instruction numbers in each application. So they can help with this part. By having new process technology, 7 nanometer or 5 nanometer, you can improve the frequency. So the frequency can be improved by the transistor devices. And in the computer architecture class, we will learn a lot of architecture to improve the cycle per instruction. So by improving these 3 parts, you can reduce the total execution time, average execution time, So in this lecture, we will focus on the CPU. I'm sorry, CPI. So the performance can be evaluated by different metrics. The first one is the latency, which is the time to complete a task. The second one is the throughput. So the number of tasks per unit time. For example, operation per second. Or multiplication per second. How many applications? How many floating point application? Floating point multiplication you can complete in each second is the throughput, and this is a very important metric to evaluate your GPU. But for each multiplication on GPU, it may have the same latency as that on CPU. So even you buy a new GPU, it can help you to improve the throughput because you can run a lot of multiplication simultaneously on your GPU. But each multiplication may have the same latency on the CPU. While your CPU can only support maybe 4 multiplication concurrently. So sometimes you can improve them both. I mean, the latency and the throughput, both. But sometimes if you want to optimize one matrix, then you have to sacrifice the other one. So here is one example to explain what's the latency and what's the throughput. Assume you have 2 cars. One small car, capacity is 5, speed is 6 miles per hour. And you can also have a bus. The capacity is 60, but the speed is slower. It is only 20 miles per hour. Assume you want to move people from A to B, and the distance is 10 miles. This is the latency. How you calculate your latency? You just use the distance divided by the speed. For the car, which is 1 divided by 6 hours. So it's 10 minutes. For the bus, it's 0.5 hour, which is 30 minutes. And then these are the throughput. So although the car has a shorter latency, but the throughput is smaller. So there's no clear answer on whether the car is better or the bus is better. You need to optimize these metrics to optimize your goals. If you have a different goals, then you need to pick up different metrics. So if I say A is faster than B, either the latency of A is shorter, or the throughput of latency, I'm sorry, the throughput of A is larger. Faster means either you have a shorter latency or you have a larger throughput. And here is the difference between the max time and X% faster. For the X% faster, you need to add one input. So for the car and the bus example, the car is 3 times faster than the bus, but the bus is 4 times faster than car for the throughput and for latency. So let's have a CPU example. So for the CPU A, the CPI is 2. Frequency is 2.8 gigahertz. For the CPU B, CPI is 1. Frequency is 1.8 gigahertz. So the CPI is short for cycle per instruction. Cycle per instruction. If you have a smaller value, which means the cycle per instruction is shorter, which is better. So based on the CPI, but for the frequency, A is better. Then you need to calculate whether you want to choose A or B. So one example is 800 megahertz Pentium 3 is actually faster than 1 gigahertz Pentium 4. So you can add 2 latency values, but you cannot add 2 throughput values. Again, we will use the a distance, a speed. So this is the distance, and this is the speed, and here is the latency for the first one, and here is the latency for the second. So you can actually add these 2 latencies. The latency is also execution time. Add them together. But for the throughput, you cannot do the addition. Six hours, 30 miles per hour, 2 hours, 90 miles per hour. This is the total distance. If we want to compute the speed, then we use a different distance divided by the time. So this is the throughput.
So for the processors example,
Yes.
would the throughput of A be 1/2?
So for this example, you should use the Ernst law. This one. So assume you have the same application. So this part is what for both of them. And then you just use the plug your frequency and your CPI.
So you're not interested in finding the throughput of it.
No. This is the latency. This is the latency
Oh, yeah.
of each application.
Oh, and the instructions for program. Okay, I guess.
I mean, you can use that law to compute the,
Yeah.
this part. Again, if you have a multiple benchmarks application in a benchmark suite, some salesman want to sell you some computers. In order to explain how good their computers are, they need to present some benchmark performance. How to compute the average performance is also, they also have different metrics to compute the average performance. For example, the first one is the arithmetic average. Second one, the harmonic average. The third one, geometry average. You have different types of average. But generally, you guys only use the first one, arithmetic average, which actually is not a good metric when you buy a computer. Why? Because in one benchmark suite, you have a lot of benchmarks. If this CPU achieved very good performance on only one single benchmark, but did a relatively bad job on the other benchmarks, the average, the arithmetic average can be also very good. In another way, I should say the average salary of you and Bezos is very high, but this number is meaningless because you have no money. Bezos is the richest man on the earth, right? So in this case, geometry average is better. Better metrics you need to pick up in order to evaluate, so what's the performance of most benchmark in that suite? So in order to improve the application performance, we have two localities in computer science. The first one is temporal locality. Means if you look something up, it's very likely that you will look it up again very soon. The second one is the spatial locality. If you look up something, it's very likely to, it's very likely that you will need its neighboring elements. and then we have power and energy. So power is evaluated by is expressed in watts. And the energy is the latency multiply the power. For example, second multiply watts. So the power can be represented by of the curve. But the energy is actually the area of this part because it's a time multiplied power. So when you talk about smaller energy, my computers consume smaller energy. You need to explain whether your computer have a smaller power or your computer has a larger power but a shorter latency. So smaller energy does not necessarily indicate a smaller power because the power can be the same or larger, but the latency is shorter, much shorter. So nowadays, all the computer systems from your mobile phone to the data center are constrained or limited by the energy consumption. They need to spend the power in computing power and also cooling power for the data center. So the total power consumption can be very significant. So all the power consumption will be converted to heat. That's the reason why you need a cooling power. And the cooling in itself also consumes power. So if you cannot dissipate those heat soon in very fast speed, then the chip may fail because of the characteristic of the transistor. So higher temperature will reduce the reliability of your computer. It may increase the errors on your hard disk or NAND flash. It also may generate some errors on your CPU. So the power is can be divided into two parts. The first one is a leakage power. The second one is a dynamic power. When you power up your computer, no matter you use it or not, you will pay the leakage power. But only when you run some very heavy workload, you have the dynamic power. So you can consider the transistor like a switch no matter you open or you close your switch, you will pay the leakage power anyway. But only you change the switch, you pay the dynamic power. And this is the equation for the dynamic power. It is related to the frequency and the supply voltage. So the power limitation also limits your frequency, because you cannot have a very large F. Otherwise, the dynamic power will go beyond the budget. And the static power is proportional to the VDE and also the temperature. So if your computer is very energy consuming, it will consume a lot of power. So this power will be converted to heat. If you cannot do the cooling well, then the temperature of the computer will goes up. Then the leakage power also will goes up. You will spend more power on the leakage power. Why? Because your leakage power or static power is proportional to this value. And this value is has this T here, indicated the temperature. When the temperature goes up, the leakage also goes up. It will consume more powers. More powers will also bring your temperature up more aggressively. So this is a positive feedback loop. That's the reason why the data center will spend a lot of money or a lot of energy in the cooling part. So in the early age of the transistor design, they can keep the so-called ideal scaling. In the ideal scaling, they can always reduce the VDD and the capacitance. So in this way, they can improve the frequency. And reduce the dynamic power. If you have the same power budget, then we can improve the frequency. But nowadays, the VDD does not scale. So you cannot simply put that on the new generation of physical technology. So for example, now if you have a, let's say, 3 nanometer process technology, you may have the same VDD. So in this way, you cannot reduce the dynamic power. Even you have the, a new generation of process technology. So here is one example. 386 only consumes. But for i7, consume 130 watts. And this is the typical area of the chip. And my 130 watt is the maximum power consumption you can have in such small area. Otherwise, you need more advanced cooling devices. That will increase the overall cost of your personal computer. Can you increase the area of chip? No. Why? Because we learn the yield, the area, the relationship between the area and the yield. If we increase the chip area, then the yield will be lower. That also costs you more money because the price of each chip will increase. Because the VDD does not scale, the VDD does not decrease on even a new generation of process technology. We cannot further reduce the power anymore. So this is so-called power war. Then we need to reduce the power consumption. So I will briefly introduce several techniques to achieve that. So the first one is clock gating. The idea of clock gating is very simple. If you do not want to use this function unit now, we don't need to send the clock signal into this function unit. By an AND gate, we can achieve that. So if this function unit does not have clock, it has no frequency, right? The F is 0, then the dynamical power consumption is 0. So when we need this function unit, we can enable the clock. We can send the clock to this unit again. Although we need to pay some wake up latency for this function unit, but in this way, we can reduce the power consumption. The second one is power gating. The power gating means we just cut off the VDD. We just turn off that unused core or unused function unit, which is similar to this clock gate. But if we have no VDD, then we don't need to pay the leakage power either. So we have no dynamic power or leakage. We can reduce more power. But again, when we want to turn on this core, then we need to pay longer latency. Another method is called DVFS, means dynamic voltage frequency scaling. If we reduce the voltage, reduce the VDD, lower VDD cannot maintain a higher frequency. So if we reduce the VDD, then we reduce the frequency. When you run some application, you don't need your call run at 100% frequency all the time. So the software, the operating system may observe some opportunities to do the DVFS. It will, if your application is not so busy now, it will reduce the voltage VDD, and then In this way, it can reduce the frequency. So your application can slow down because your application is not always busy anyway. By reducing the voltage, reducing the frequency, you can reduce the dynamic power. When you buy a CPU, it's a, let's say it's a 4.3 gigahertz. This is the maximum frequency it can run. But actually by the DVFS, the cores can be also run at 1 gigahertz or 2 gigahertz. So I briefly introduced the clock gating, power gating. Clock gating means just to turn off the clock signal. You don't have dynamic power, but you still need to pay static power. Power gating means you just turn off the complete function unit of the clock. You don't have a dynamic power or leakage power. And then we introduce the DVFS to adjust the frequency by adjusting the VDD. These are very simple techniques, which have already adopted by all your computer, your mobile phones. But we need more techniques to reduce the power consumption. Here are some examples. We can develop more new devices, for example, photonic links, new type of memory technology to reduce the power consumption. So here is the power consumption breakdown of a computer system. The CPU costs a very small part of the total power consumption. The memory, the disks, the I/O also consume a significant portion of the power consumption. So in order to reduce the system power consumption, we need a more method. Well, the instruction set architecture also have a huge impact on the power consumption. So the instruction set architecture is actually the interface between software and the hardware component. It decides how the operation implement. Which type of operation are fast and which type are slow, and which type of operations are energy consuming. So in each instruction set architecture, we have the program counter, general purpose registers, memory, and control registers, so that the program can, do some register transfer level programming. You can move the data between different registers. And the register and the instructions are encoded by binaries. So recall the first one. So now we have two types of architecture. One is a so-called CISC. The other is a RISC. So these two types of instruction set are different philosophy of this equation. So the CISC improve actually this part. It will directly provide you very complex instruction like the square instruction. So by one single instruction, you can compute a log, a square, very complex arithmetic operation on the system. So which means that it can be used this instruction per location or per program. But the RISC machine have a different philosophy. One complex operation, for example, log operation, may be compiled into multiple, let's say 5 instructions on the RISC machine. But the RISC machine will improve the cycle for and because the RISC machine instructions are very simple, so each cycle we can execute one instruction. Because the decoding of the instruction is also very simple, the frequency can be very high. Then it's very difficult to say that whether the CISC is better or weak in terms of the total latency. So generally speaking, you can see that your mobile phone is all on this. The RISC machine has a very low power consumption. But your PC and the Intel CPU are all CISC machine. So nowadays, the Intel company actually add a new layer between the machine and the instruction set. It's called a micro operation. So the so-called micro operation of the Intel company is actually the RISC. So they have 2 layers of instruction set. One is the CISC instructions, because they want to maintain the compatibility. They want to be compatible with the x86 instructions. Under this layer, they have a new layer, so-called micro operation, actually implement the RISC machines. So by the RISC machine, we have a very simple structure. We have program content, instruction fetch, data fetch, compute. Because we get the instruction ready here and the output ready here and real and store the data. Back. So this is the typical 5-stage pipeline. We will introduce this pipeline with more details in the second half of this semester. Any question?
So I'm pretty familiar with like the way the process of batch instruction, but something that I don't know is like where these instructions are in RAM.
Yes.
Okay.
They are in the memory.
So the operating system will place them.
Yes. So if no question, we can stop today. Next class, we will do the review.